One of the reasons why the world that we live in seems very complicated is that it's got a lot of variety. And when you're trying to understand something that has a lot of variety, classification is often the best way to start. Mendeleev, for instance, classified the chemical elements and came up with a periodic table. I want to talk about a classification of chemical substances, and I've singled out two classes for special attention. I've chosen them because they can teach us a great deal about chemical bonding. Here are three members of one of those two classes: iodine, sulfur, and carbon disulfide. What do they have in common? Well, for a start, they all have low melting or boiling temperatures. Carbon disulfide, for instance, is a liquid, even at room temperature. Iodine and sulfur, it's true, are solids, but let's see what happens when I warm them. A little slab of iodine goes into the cup, and the underside of the cup is gently warmed. I'll protect the iodine from drafts by lowering it into a gas jar. Now you can see the purple vapour from the gently warmed iodine. Sulfur is also a solid at room temperature. I'll warm it in a bath of heated oil. It soon begins to melt. The molten liquid sulfur is yellow, like the solid. I can take the temperature of the freshly melted sulfur by using this probe. The melting temperature of sulfur is only about 110 degrees Celsius. To understand this, let's see how the atoms in these substances are arranged. Here's a computer-generated model of solid iodine. Each iodine atom has just one other iodine atom a short distance away. If I mark these short distances by lines, this is what we get. The structure consists of pairs of iodine atoms. Each iodine atom has two types of neighbour. There's one iodine atom which is very close, but all the other neighbouring iodine atoms are further away. So in our minds, we're entitled to group the iodine atoms into pairs. These pairs of atoms are called iodine molecules. The molecular formula of iodine is I2. Now for sulfur. This time there are clusters of 8 atoms which are all close together. Here's the cluster in close-up. The molecular formula of sulfur is S8. The 8 atoms in each molecule form a puckered ring. As in iodine, the shortest distance between two atoms in the molecule is less than the shortest distance between two molecules. So, sulfur consists of S8 molecules, iodine of I2 molecules, and liquid carbon disulfide of CS2 molecules. Substances like this, out of whose structures you can pick discrete molecules, are called molecular substances. The structures of molecular substances explain their properties. The distances between the molecules in molecular substances are relatively great. That's a sign that the attractive forces between the molecules are weak. It doesn't therefore take much heat, much thermal energy, to overcome those forces and separate the molecules. So iodine melts and then vaporizes at quite low temperatures. In both the liquid and in the vapour, the molecules are still there, but they're much further apart. The intermolecular forces also explain other properties of molecular substances. Because they're weak, there isn't much difference between the forces acting between two iodine molecules and those between an iodine and a carbon disulfide molecule. So, if iodine is dropped into carbon disulfide, the attractions between the carbon disulfide and iodine molecules are quite likely to pull the solid iodine apart. Let's see the experiment. Here's some liquid carbon disulfide. In goes the iodine. It dissolves instantly and gives a purple solution. What happens to solid iodine also happens to solid sulfur. The S8 rings separate from each other as the sulfur dissolves in the carbon disulfide. Liquid molecular substances often dissolves solid molecular substances. Now I want to look at the other class of substances. I've got 3 examples of it: potassium dichromate and 2 alkali metal halides, potassium iodide and sodium chloride, common salt. They're very different from molecular substances. For a start, they have much higher melting and boiling temperatures. To melt an alkali metal halide, I need a very hot flame. Even then, it's difficult, so I'll use a mixture of 2 halides. This melts at a lower temperature. Even so, a lot of heating is needed to get results. Gradually, liquid starts to appear. Eventually, melting becomes much more widespread. I'll keep this hot for a moment while I switch to another molten substance that you've already seen, a molten molecular substance, liquid sulfur. I'll test its conductivity. 2 probes are wired to a power supply, an electric bell and a lamp. Now I'll lower the probes into the molten sulfur. Not a peep. Molten sulfur doesn't conduct electricity. Now the probes go into the molten alkali metal halide. Not much doubt about that. Molten alkali metal halides do conduct electricity. To try to understand this, let's look at their structure. If you want to play the atomic sculptor, you can cut various shapes from the sodium chloride structure. This one's a cube. The sodiums are red, the chlorines are green. But whatever shape you choose, inside there's a simple principle at work. Around each sodium there are 6 identical chlorines, and around each chlorine there are 6 identical sodiums. All 6 are the same distance away. From each sodium, all the surrounding chlorines look the same, so there's no justification for singling out one of them and identifying an NaCl molecule. Sodium chloride is not a molecular substance. So what sort of a substance is it? The conductivity of the melt points the way forward because, like the conductivity of salt solution, it suggests that ions are present. The sodium ions are positively charged and the chloride ions are negatively charged. Now suppose that these ions are also present in the solid. What sort of a structure will they take up? Well, the positively charged sodium ions will attract negatively charged chloride ions from all directions. And the negatively charged chloride ions will attract positively charged sodium ions from all directions. So the sodium chloride structure is consistent with an ionic composition. When sodium chloride melts, the ions become sufficiently detached from each other to form a liquid, but they're still there. Because their properties are consistent with the presence of ions, substances like this are called ionic compounds. The attractive forces between the oppositely charged ions in sodium chloride are much stronger than those between the molecules in iodine or sulfur. That's why the melting temperatures of the alkali metal halides are so high. Those strong forces also resist carbon disulfide. When I add salt to carbon disulfide, little, if any, dissolves. So everything seems quite logical, but there's a joker in the pack. It comes in the shape of water. So what's so peculiar about water? Well, if the forces between the ions in solid sodium chloride are so strong, why does it dissolve so easily in water? And if the forces between the molecules in solid sulfur and solid iodine are weak, why does water dissolve so little of them? What this suggests is that water is a very remarkable substance, and that's one of the two things that I'd like you to take away from this sequence. The other is this contrast between molecular substances and ionic compounds. As you'll find out, it was by focusing on that particular contrast that scientists first arrived at productive theories of chemical bonding.